All right, so in this one, we're going to learn about conformations for alkanes, and conformation is a very specific thing limited to single bonds. So what is it about single bonds that make conformations? And about single bonds is that you can rotate single bonds, okay? So two things here, rotation and then single bond. So rotation is only like moving it around while it is still bonded. So you're not breaking any bond. And then single bond meaning that you cannot do this for a double bond, because if you do this on a double bond, you will end up breaking it, okay? And so we do this only for single bonds, regardless of functional group, okay, in there. So whether you have an alcohol or an aldehyde or a ketone or ether, it doesn't matter. So long it's a single bond, you can rotate that. All right, so important thing is you're rotating it, and that gives you conformers. Okay, that rotation gives you different conformers. So any kind of an sp3 bond is going to do that. All right, by the way, let me just remind you, since I have the cis and trans isomers here also, is because we've done two kind of isomers before, constitutional isomers and then cis and trans isomers. In both of them, you had to break bonds in order to make something new. Even to go from cis to trans, you actually have to break an atom, break a bond in order to, change it to give you the trans isomer. All right. So, this conformation is just about rotation. You cannot break any bonds in here. So we will do this both for straight chain as well as for the cyclic compounds. Now in cyclic compounds, you can't rotate the bonds because if you rotate, you will break them, right? So our movement of the bond for cyclic compounds is going to be slightly different, okay? Conformation or conformation analysis, as we call it, is a very 3D kind of a thing, okay, that we do. You have to imagine molecules in 3 dimension. And so for this reason, I have various videos in this, and I don't have the videos incorporated in this PowerPoint, otherwise it will become too long and also too big. Okay, so I have given you the links for the videos, and I'll keep reminding you that this is the video you should watch, okay? Because in a 3D, you kind of have to either have a model set with you so you can visualize all of these things, or you can watch the video, okay? That should help you out. But before we do all of that, let's go ahead and learn some terminology, because yes, there's important terminology here as well. So dihedral angle is the first thing, and dihedral angle is the angle where you're looking at two groups on adjacent atoms. Not on the same one, because for the same one, that angle is determined by the hybridization. So for example, if you're looking at the first one here, this atom, if you're looking at this one, you know what the angle here is going to be. It's 109, because for sp3 hybridized, which is all the single bonds that we are studying, the angle is 109, at least for carbons over here right now. So what we look at is the dihedral angle between two carbons. So here is carbon number 1, and here is the carbon number 2. So this is joined together. So this carbon, this circle, this is a carbon here, and that also has the 3 bonds on it. So you're looking at the relationship between the two atoms on adjacent carbons. Okay, so here the angle is 160, here it is 0 degrees. This angle from here to here is 180. So just depending on what kind of two groups you're looking at, or which two groups you're looking at, that will give you the dihedral angle that you're looking for, okay, or that you're studying. But dihedral angle is the angle between two groups on adjacent carbons, not on the same one, adjacent ones, okay? All right, so the next thing is the steric strain, and steric strain is caused by big atoms. Okay, so when you have large groups or large atoms would mean something like bromine or iodine. Large groups would mean things like ethyl, propyl, or t-butyl groups. Those are really big. So when you have those huge groups next to each other, they cause a steric strain. And steric strain means there's some sort of a crowdedness going on. So for example, if you get into an elevator, and then just too many people come in, so which means to get out, from the elevator, you kind of have to work your way from the back to the front or whatever, especially if you're at the back. So that's kind of a crowdedness in there, okay? And that's called steric strain. And then there is a term called angle strain. Now, when we do hybridization, when we learn about hybridization, we know that each hybridization has its specific angle, okay, that one should have. But when you have cyclic compounds, then cyclic compounds sometimes don't have a choice because they have a ring structure and they have to follow the angle that is given in that ring. And that ring angle may not be the same as what is supposed to be because of the hybridization. So which means that if it is not the same, if it is less or more, well, in that case, you have an angle strain. Okay, so when two things don't match up, you end up having some strain. Okay, so these are the three terms that we will be talking about as we go on. So here is your first video to watch if you want to learn about these three terms as far as, visualization is concerned. So I've made a video. The first molecule I want to look at for conformation is going to be ethane. It's a simple molecule, 2 carbons, 6 hydrogens. That's all there is to it. But the main thing I want to show you here is going to be the 3D structure, okay? Because as I said to you before, the 3D visualization of molecules is really important here. Not only do you have to be able to see that molecule in 3D, you have to be able to draw the molecule in 3D when you're writing it in your books, okay, or in your notebook. So we have two kinds of projections that we draw, Fisher projection and Newman projection. So I'm going to show you how to do this, and all this introduction is for next slide. So I'm talking, so I'll show it to you, but you can read it otherwise, all right? But hopefully you will not need to read it because you're listening to me. All right, so here let's look at ethane. Now ethane is a small molecule, as we just said. So here you have 2 carbons with the hydrogens on it. And here what I've shown you is the ball and stick model for the same molecule. The top molecules here, these are called the Fisher projections. Sawhorse projection also. In this case, what you end up seeing is like the sawhorse on, a playground or something where you have the seat right here and the, the bench. But anyhow, and so these hydrogens, you can see this one is going up, these ones are going down. They have to be all proper angles. In a 3D, you have to show proper angles, okay, for any kind of molecule drawing that you're doing. So here everything is sp3 hybridized, so I have to show the 109 angle, which is what I'm showing here as well, okay, so with the ball and stick model. So now what we do is in conformation, we have to rotate, okay, the bond. So the bond we are rotating is the carbon-carbon bond. I mean, if you rotate the carbon-hydrogen bond, you're not really doing a whole lot. So when you rotate the carbon-carbon bond, now all the groups on the carbon are also going to rotate with it. So that's what we are doing over here. And you can see, what I've done here for you is the front carbons. Their hydrogens are just a little bit darker, okay, so you can see what happened here. So this again is the sawhorse projection of the rotation. So now this hydrogen is over here, this hydrogen is down here, this hydrogen is up here. So that's kind of what happened here, and this is the ball and stick model for it, okay. Now, if you're having trouble visualizing as to seeing like, oh, this is the relationship between the two hydrogens here, then, it's a normal thing to have those kind of problems. And for that reason, we have what is called the Newman projection. In the Newman projection, we kind of focus on just the 2 carbons, okay? And which 2 carbons? You decide which 2 carbons, which in this case, we only have the 2 carbons. So the front carbon is 1 carbon and the circle is the back carbon. So which means what is joining here, which is invisible also, is the bond between the carbon and carbon, okay? But you only look at 2 carbons at a time because, again, remember the dihedral angles and all that we talked about was only between 2 carbons. So you look only at the adjacent carbons. And so in ethane, we have no problem going 2 carbons. So again, the lighter atoms are at the back, and you can see that the lighter atoms I've drawn here, at the bottom here. So in a triangle, and here are the lighter atoms, okay, for the back carbon. The front ones are a little bit darker, so you can see them over here. Okay, once you do the rotation, okay, of the front carbon, and that's what I have done, is the front carbon I have rotated. So now what happens is that the dark blue hydrogen that has moved up to the top over here. So in this case, in the Newman projection, you can clearly see what's going on with the dihedral angles, okay? And you can just zone in on the atoms you want to study rather than looking at the whole molecule or getting confused by, you know, what the angles might be and so on. So, you know, it's much easier. Again, you should watch the video that I have here for you to show you how the rotation is happening and what the visualization might be in a 3D. Okay, and this is just for ethane, so only 2 carbons in there. So now let's look at butane, which is not a hugely complicated molecule, but definitely bigger than ethane because it has 4 carbons in it. So once you have more atoms, then you can study more interactions between the atoms. Because remember, when you study conformations, the most important thing is what's going on between the atoms. What is the dihedral angle? What is the angle strain? And that happens when you have more atoms or bigger atoms. Okay, so something like ethane was not going to have much interaction anyway. Okay, so here I have the 2 conformations for butane, all right? And again, I've color coded everything. So the back one is blue, the front one is pink, okay? And I didn't move the front one, okay? So the front one remains the same. I moved the back one. That's kind of my thing, what I do. So when I'm rotating only the back carbon, okay? Not the front one. Okay, so first let me just kind of talk to you a little bit about what are we rotating here, because remember when we said we are studying conformation, you study the conformation for rotation of only 2 atoms in there. So which 2 atoms are we looking at here? And the 2 atoms we are looking at is carbon number 2 and carbon number 3. Okay, so which means we are rotating this bond. And if you're wondering why we're doing that, why not looking at 1 and 2? And that's because carbon number 1 has 3 hydrogens. 3 hydrogens are not going to have that much of interaction or steric strain with any of the other atoms in there. Only when you have 2 and 3, which now have bigger groups on them, they're going to have interaction. Okay, and the groups actually are not really some other groups that you have added on or anything. It's just part of butane, right? So carbon number 1, 2, 3, 4, that's the chain. So even within alkane as a chain, you can have interactions, okay? And you can have conformations, which is why we're doing this. But anyhow, so what we are doing now is we are going to rotate the bond between carbon number 2 and 3. And again, remember carbon number 4 is going to remain steady on the top. Okay, so you will see carbon number 4, which is my front carbon. Okay, number 3 is my front carbon. That's going to stay steady. Okay, that's not going to rotate, only the back one is going to rotate. So that's what I did. So the first conformation that I have for you is the Fisher projection, which shows you the relationship between these 2 carbons, which is right behind each other right here. And then once I do the rotation, and I rotated 180 degrees, and now the CH3 groups are opposite each other. Now you can see that in the Fisher projection also, but you can see much clearer in the Newman projection how the CH3 are related to each other. Okay, to see the interaction between carbon number 1 and 4, for a Fisher projection, you kind of would like, can I just move a little bit, so I can see the carbon, interactions. So Newman projection actually takes care of that because it puts the 2 carbons right in front of each other. And that's how you're able to visualize what's going on as far as the 2 big groups are concerned. Okay, so here the dihedral angle is 0. Here the dihedral angle between the 2 big groups is 180. So when we look at all these conformations for butane, okay, what we do is what I have done before was just, rotated by 180 because I was just making a point to show you how the rotation is done. But when we write the conformations of butane, we don't just rotate it 180. We actually rotate by 60 degrees at a time. Okay, so which means 360 is a full circle. So you're going to have 6 conformations. Okay, so you end up getting 6 structures from one structure or one rotation, one full rotation. All right, so 60-degree rotations is what we do. Then here are some new words for you, because I know you were thinking I haven't learned something new, in a while. So there are going to be three structures we are going to look at: eclipsed, anti, and staggered or gauche. Okay. Eclipse conformer is going to be when the dihedral angle is 0 degree between the two big groups. Okay. Anti is when the dihedral angle is 180 between the two large groups. Eclipse now doesn't have to be between the two large groups. It could be between any groups, but usually we study the large groups, right? Because that's the one that's causing the most steric strain. So eclipsed, you will see as we'll go on, you will see that eclipse can be for smaller groups also, but it's the bigger groups when they're right behind each other. That's when they really cause the dihedral angle to be 0, and a little bit of a problem, okay, for the molecules. Anti for sure is going to be when the bigger groups are 180. 180 means as far away from each other as possible. Okay. The staggered and the gauche is when the groups are sort of away from each other, but not so away from each other with a 60-degree angle. Okay, so it's not so much. So let's go ahead and draw all the butane structures out and see what it means. So here we have all the 60-degree rotations for butane. Now, what I do for my structures is I keep my front carbon, as I said, steady. I don't move that. It is the same, and I just move the back carbon. Okay, this is my habit. You can have it the other way around, which means you can keep, the back carbon steady, which is the blue one here. You can keep that steady and move the front one. It's entirely up to you, and I've shown you how to draw the structures also, but that's what I've done here. So that way at least you're not moving two things at the same time. All right, so the pink carbons are steady, they're in the front. So now what we do is we take the CH3, which is the eclipsed over here, which means the 0-degree dihedral angle. So I've labeled it here for you. This is eclipsed, and now we're moving it 60 degrees. Another 60 degrees, another 60 degrees, another 60 degrees, and another 60 degrees. Okay, so it's 60-degree rotation. So we have 6 structures. All right. Eclipse is going to be the one in which the big groups are right behind each other. Now you have this eclipse also, where you have groups directly behind each other, but these are not what we call true eclipse. And I'll tell you what that means in terms of energy. Okay, in just a second. I want to talk about the staggered also. The staggered or the gauche, okay, you can call them either, it's fine with me, okay. The staggered and the gauche, or they're both the same things, is when the big groups are at 60 degrees to each other. So you can see number 2 and number 6, okay, they are pretty much the same. So they're kind of just reflections of each other, right? But it's the main thing is that the angle between the two big groups, okay, that's 60 degrees, all right. And then here is the beautiful anti, where the big groups are opposite each other. All right. So again, 60-degree rotations for each of these as you go on. So I've listed here which structures are the same, which are different, right? So for example, the 2 eclipse are going to be pretty much equal over here. This eclipse is going to be different from the other 2 eclipses, because in the first eclipse, the 2 structures, which are the 2 groups that are big, are right behind each other. Okay, so that's why this eclipse is going to be different. Now, energy wise, when the 2 big groups are right behind each other, that is going to be the highest energy structure. Highest energy means it's not very stable. Okay, it's going to want to go away from there. Consequently, you can tell what the lowest energy is going to be is when these groups are the farthest away from each other, which is then the anti. Okay. Now the 2 eclipses, which are number 3 and number 5, those are going to be high in energy also. Okay, but not as high as number 1. And then number 2 and then number 6 over here, the 2 staggered, they're okay. They're not that bad. Okay, as far as energy is concerned, but anti is the lowest in energy, because you can see they're going to be very stable. The large groups are far away from each other. So here I've written the structures out again, but I want you to go ahead and look at the video that I have for you in the links and see how you can, visualize all of these things in the models, okay? Just remember my directions for drawing these structures. Be consistent. I've said that before also, when you draw constitutional isomers, similarly with conformers, be consistent. You don't have to use different colors. You can if you want to. It's a little tedious. I'm okay with you using the same color, but I'm not okay if you rotate both of the atoms, okay? So either rotate the front carbon or the back carbon. Here is the energy diagram, okay, for this. And yeah, I drew this graph out, so that's why it looks a little funky, but in any case, it doesn't matter, because the main thing I want to show you is that the eclipse is the highest energy and the anti is the lowest, okay? Now, here is another thing that I just want to mention to you before I go on, is that when you draw these conformations, do you start with the anti or do you start with the eclipse? Okay, it's entirely up to you also how you do that. I don't know why I like to start from the eclipse, and that's why you will see my structures at the, in the previous slides all starting from the eclipse, is because I like to have my two groups at the back, so I know that this is going to be my highest energy, and then I start the rotations. Okay, that's how I go. So these are 7 structures only because I have 2 antis over here, but otherwise there should be 6 structures, okay, in general. But this is the energy graph for all the conformations for butane as predicted. Okay, so let's look at a problem over here for writing conformers. All right, so draw as many compounds as you can that are alcohols with the formula C4H10O, because remember, when you're drawing constitutional isomers for oxygen, you can also have ethers. Okay, so I specified here for alcohols. Draw the conformation of one of these constitutional isomers and label them and identify the highest and the lowest energy conformers. So, so many things going on here. Okay, so first of all, we have to draw the constitutional isomers for C4H10O. So here are the constitutional isomers. And then we are going to pick one of the constitutional isomers for study. Okay. Actually, I have done more than one of them, but this is the first. Okay. And so here, let's look at the first one here, which is a simple alcohol, the first one with the alcohol at the end. Okay. So this is the one that we're going to focus on. But the most important thing is, what are we focusing on? So I labeled my carbon number 1 as the one with the alcohol, because according to what we have learned about nomenclature so far, you have to start numbering where the functional group is. Okay, so that's what I'm just doing over here. So the best carbons to study here would be 1 and 2. We can do 2 and 3 also. I think I've done that in the next slide. Okay, but number 4 and 3 would be not very useful for us to study because 4 has only the 3 hydrogens. Okay, so this is also a part of decision making for you to decide, which 2 carbons to study. So we're going to choose 1 and 2, okay, for this problem. Now we have to see what carbon number 1 has. What kind of groups does it have? Okay, and so I've written over here for you that carbon number 1 has the OH group, of course. It also has the hydrogen and hydrogen, right? Those invisible hydrogens, those are right there. And carbon number 2 has the CH2, CH3, which is all of this group. And then it has the 2 hydrogens, okay, over here. So which means when I draw my first conformer, then I know what to put on those 2 carbons, because remember, my 2 carbons that I'm looking at is carbon number 1 and carbon number 2. Carbon number 1 has the OH and the 2 hydrogens, and carbon number 2 has the CH2, CH3, and then the 2 hydrogens on there. Okay, so that's the reason I had to write these groups out, and hopefully this will become easier for you. So you don't have to write it like this, the way I did, but in any case, it's there for you. Okay, so once you've identified your carbon number 1 and 2 that you're going to see, and then you put the groups around there. And remember what I said, that I start to, I usually start with my eclipse, okay, because then I know my groups are right behind each other, and then I just draw 60-degree, 60-degree, 60-degree rotations, and then I keep moving around, okay. That's kind of my thing. I also keep my first carbon steady. I don't move that, so you can see my OH is on the top for the front carbon, and I'm rotating only the one behind, okay. So first of all, you just go ahead and write all the structures out, okay. Now I'm sorry that some of these structures are kind of melting into each other because the CH2CH3 group is quite big. Now, if you wanted to, you can write ET, okay, for ethyl group here to kind of, stop all that crowdedness, stericness, in there. But when you write ET, you kind of lose the meaning of the big group, okay? So it's a good idea to go ahead and write the whole group out so you can actually see how big it is, how bulky it is. So it is easy for you to figure out what is going to be the lowest and the highest energy structures, okay? I mean, if you're okay with understanding that ET is actually 2 carbons, then, go for it, okay? No problem. All right, so here are all the groups, and now when we're trying to figure out which is going to be the most stable structure, then I will first look at my eclipse, because I start with my eclipse being the highest energy one, because I put the big groups at the back, and then I will come to the anti, and then I'll see if I have the big groups right opposite each other. Now sometimes they're not, that's not the lowest energy, but in this case it is, so I am all set, okay. The other question here was that I had to label all of the structures, so I've done that: eclipse, staggered, and eclipse, and then anti. These eclipses are not true eclipses, as we know, but still that's what they're called. And then I've also labeled the lowest and the highest energy conformers, okay. So I am all set to go ahead and get my 100% on this problem, okay. All right, so the next problem that I have here is pick any 2 other structures from the isomers from the alcohol from the previous problem, and then decide which conformers to look at. So in this slide and the next slide, that's what I have, okay. So here I have, the second structure where the alcohol moved from the first carbon to the second carbon, all right. So what I've done here in detail is gone through and looked at what are the groups that are attached on each carbon, because that is something you have to do in order to figure out what 2 carbons to study, right, as I was saying before. So again, for carbon number 1, if you were to look at carbon number 1 and 2, so carbon number 1 would have 3 hydrogens, carbon number 2 would have OH, it would have the CH2, CH3, and then the third thing is the fourth one is the hydrogen, okay, because this is the fourth one. So the third one is the hydrogen. Then carbon number 2 and 3, what are we looking at carbon number 2 and 3? Carbon number 2 is going to have the OH, right, the CH3, the CH2, CH3, and then the fourth one is the hydrogen, okay. And then carbon number 3 is going to have 2 hydrogens and a CH3. All right, carbon number 3 and 4, if you're looking at, so number 3 has this whole big group on here, and then 2 hydrogens, and carbon number 4 has 3 hydrogens. So obviously I'm not going to look at carbon number 4, okay, which means carbon 3 and 4 are out. So we either look at 1 and 2 or 2 and 3. Okay, so that's what we do over here. So which one did I do over here? So I did carbon 2 and 3. So I took the central 2 carbons here. Okay, now this question doesn't really require for me to draw all the structures. So I just have to draw the lowest and the highest energy conformers. So for carbon number 2, I have the OH, I have the CH3 and the H, the pink ones. Okay, and at the back, carbon number 3, I have the CH3, and then I have 2 hydrogens. Okay, so in the highest energy conformation, I have to make them eclipse. So I have to put 2 groups at the back. Okay, 2 big groups right behind each other. Dihedral angle is 0. Now in this case, the lowest energy group is not exactly going to be anti, because there is no structure that I can draw in which two groups are going to be completely opposite each other, okay, because I have three big groups. So the only thing I can do is I can say, okay, well, this is going to be the lowest energy because this is the farthest away I can put all of these, okay, that's it. So it's not that the CH3 is opposite CH3. If the CH3 was opposite OH, then also they would be closer, okay, to each other. So it's fine. They will probably be equal in energy if the CH3 was here versus there, okay. So you pick and choose, okay, which one is going to be your lowest energy, depending on, you know, how far away you can put those groups. So here is another one. I've took another structure, the third one, I think. And then I've shown you the structures. I think you can do this yourself. So look through it and let me know if you have any questions. Okay, now the CH3s are actually on the second carbon. The first one has only OH and the two hydrogens. The back one has the two CH3 groups. Okay, so go through this. All right, now for cyclohexanes. Cyclohexanes are very interesting, not cyclohexanes, cycloalkanes are interesting because we have ring structures now, okay? So the smallest ring possible is 3 carbons, giving us cyclopropane. Now here we are going to have a little bit more issues, okay? So we have the angle strain that we talked about. We have the steric strain that we talked about, the torsional strain here, which is the new word for you, which is going to be from the CH bonds, okay, on adjacent carbons. So it's almost like having the dihedral angle to be 0, right? That's kind of what this means. So those are the new, not exactly all new terms, but the one new term, which I don't think we're going to use as much, but we'll see, okay, how it goes. Now for cycloalkanes, there's going to be some other things to consider. So let's go ahead and get started before we get into conformations. So first of all, these are the structures, okay? I drew out the ball and stick models here for you also, so you can see what they are, what they look like, kind of. So all of these structures, this is cyclopropane, cyclobutane, cyclopentane, okay? And what I've drawn here, of course, with the little thing here is to show you the angle, because cyclopropane has an angle of 60 degrees, just because of the structure, okay, the way it is. But the carbon here is sp3. So if it is sp3, then it is supposed to be 109-degree bond angle. So if it is supposed to be 109, but the bond angle is only 60 degrees, this is a highly stressed out molecule. Okay, so this is a little bit of a problem for cyclopropane. The same thing happens for cyclobutane also, because again, you have a 90-degree angle just because the structure is a 4-carbon structure. So just by the nature of that, it's a 90-degree. When it is supposed to be 109 because it's sp3 hybridized. So which means we have angle strain here also, okay? Cyclopentane is a little bit better, okay, because the angle is getting a little bit better here. So this is a little bit better, all right? Now all of these structures, the first one, the second one, the third one also, but not so much, okay? But the first two structures are actually what we call planar structures. Planar meaning they are completely flat. Cyclopentane, not so much. You can see it's kind of coming out here of the plane a little bit. And so this one is what we call puckered. And so it's slightly bent, okay? It's not exactly flat, all right? So these are some of the natures of these three. I have cyclohexane in the next slide. So cyclohexane, which is this, is actually the happiest of all molecules, okay? Of all the ring structures that we have, this is going to be the most stable structure. The bond angle is about 120, and it is really, really most stable ring, and followed only by the 5-membered ring, okay? 5-membered ring also, there's no angle strain and stuff like that. So those, 5 and 6-membered rings are going to be the most stable rings. What I've shown you here, because we're going to study this a lot more, is all the different ways you can draw the structures, okay, for cyclohexane. This is the 2D structure. This is what we end up drawing all the time for cyclohexane, a hexagon, right? But in reality, when you draw the model out and look at it in a 3-dimensional structure, this is what it looks like, okay, which you're probably thinking, what the heck is this? I can't really see. This is what it is. This is what the carbons skeleton would look like without the hydrogens. Okay, so this is the 3D model of it with all the hydrogens. So this is the actual model that it would look like, and then here is what it would look like without the hydrogens. Now what does it look like? It kind of looks like a chair. Okay, so right here, this is the legs, this is the back. Okay, so it's a lazy boy chair kind of a thing. This is cyclohexane. Okay, so a little bit different, definitely not planar. Okay, definitely not planar. It's not flat at all, and a very happy molecule. Okay, I have two videos here for you to watch, and one is to understand the ring structures, really what they're like, and the second one just explains cyclohexane to you because it's really important for you to understand what cyclohexane is. Okay, so watch those videos to understand how this structure is formed. Okay, now for the conformation. Now with the ring structure, you cannot really rotate any of the bonds because if you rotate them, they are going to break. All right, so in cyclohexane, we don't talk about rotation of the bonds. We talk about flipping, okay, of the bonds. Now, cyclopropane, cyclobutane, I don't know why I have butane here. I think it's a spelling error, so we'll correct that eventually. But cyclobutane, cyclopropane, cyclopentane don't really have that much of conformations, and you're probably saying thank God for that, which is fine. That's okay. So they don't have that many conformations because their structures are planar, okay, pretty much. So you don't really get a whole lot of stuff going on with those three. But cyclohexane, on the other hand, they can flip around a little bit because they're a little bit more flexible. So they flip. They don't, as I said, they don't rotate. Okay, so they kind of flip around. So here is the chair conformation of the cyclohexane, and which is why I said that you should definitely look at the video that I have for you for cyclohexane. All right. When you start flipping it, which means you're only moving the bond. So in that case, what happens is that this bond goes up. When this bond goes up, you get a boat. Okay. When you want to go to the other chair conformation, look at this chair conformation, look at that. It kind of looks like a mirror image, doesn't it? So when you go from here to here, this is not really a mirror image. This is actually flipping the ring. So you have to go through all of these structures in order to get to the chair conformation. So one chair conformation, the other chair conformation. What are these in the middle then? Are these conformations? They are. Okay, but they're not studied as much because both all three of these are very high in energy. Okay, as we will see in a minute. But these are high in energy. So we study this chair and this chair conformation. And then if you're thinking, but they look the same, well, that is what this conformation study is about. Okay, so first of all, here's the energy diagram. Okay, so here are the two chair conformations, okay, opposite to each other going through the boat and the twisted boat. So just the name twisted tells you that it's going to be high in energy, right? The boat, you would think, okay, it's going to be low in energy, but again, I have the cyclohexane 3D model for you, so make sure you look at that in order to understand how the flipping is occurring and why the boat is not so, so stable as we think it should be. Okay, it's only these two chair models that are going to be the more stable structures and the lowest energy structures. So when we say that you're studying the conformation of cyclohexane, it is one chair to the other chair. That's it. So first of all, here is your little tutorial for how to draw the chair conformations, okay? Because drawing a proper chair conformation is a study in itself, okay? So I've shown you by numbers and by colors how to do it, but really this is what's going on. See how simple that is? You know, make sure you join the bonds, okay? So it's not all that hard to do. It's not coming out right because I'm writing in a little bit different way, okay? But otherwise it's really quite straightforward. Draw two lines, draw another two parallel lines, and draw the third parallel line. There you have a beautiful chair. So that is how you draw it. So I'm not going to go over it because it's right there for you, okay? So all the instructions are there. Make sure that when you give me all these cyclohexanes, they are pretty structures and not some, zigzag thing that I'm getting. Okay, so what happens is that when you have a chair conformation, we have hydrogens going in a particular direction. Okay, so there are 12 hydrogens in a cyclohexane. All right, so those 12 hydrogens will be going in a very specific directions. Okay, so 6 of the hydrogens are going axial, they are going up and down. So these are the axial hydrogens. Axial, you can think about it as axis of the earth going, you know, vertical. So that's the axis. See, if this is going up, this is going down. This next one is going up, the next one is going down. So up, down, up, down, up, down. That's how it is, alternate. And then we have 6 hydrogens that are equatorial. Okay, so I've drawn the equatorials also for you. So equatorials means like equator of the earth. So going down, going up, going down, going up, again alternate. Okay, going down. It's a very slight angle. Okay, but it is going down, this is going up, down and up, down and up. Okay, that's how it's going. Now you combine these two structures because, you know, you don't just have equatorial or axials, you have 12 hydrogens. This is what it would look like. Okay, so now I want to show you one thing over here that is also here, but you know, just a little bit more detail, and that is that look at this carbon that I'm focusing on. Okay, where my pointer is. This hydrogen, the axial is going up, the equatorial is going down. In the next one, the axial is going down, the equatorial is going up. In the next one here, the axial is going up, equatorial is going down, right? Alternate up and down, alternate up and down, alternate up and down. Okay, so that's how it is. And that's how all these hydrogens are in a cyclohexane. Okay, and there is nothing you can do about it. Okay, because this is the nature of cyclohexane. You just have to study it. Okay, that's all it is. Okay, now one more thing, okay, to go on before I go on to the next slide, is that look at the dihedral angle between the pink hydrogens. The pink hydrogens next to each other, they are all at an angle of 180, which remember just now when we talked about the conformations of butane and whatnot, the 180 is opposite each other, right? Anti. The angle between the dihedral angle between the equatorials, 60 degrees. Okay, that's all it is. So again, you have to see the video, okay, that I have for you, and that will show you that these two are at 60 degrees to each other. So not exactly anti, right? Yeah. Okay, so now if you're wondering, okay, let's go ahead and do the conformation, right? What's going on with the two chair conformations? So this is what's going on in the chair conformation. Again, watch the video, okay? I will tell you, I mean, if you don't watch the video, it's gonna make sense, but it's gonna make much more sense in the video, okay? So watch the video that I have for you, and I have 2 other links here for you that you can go to. Of course, these are only available in the PowerPoint, right? So not on this YouTube video. Okay, all right, so what happens when you go from one chair to the other chair? So remember one thing, okay, the one chair is facing this way, right? That is how the one chair is. The other chair is going this way, right? That is how these two chair flips are. They're kind of, as I said, they're opposite each other. They're not exactly, you know, mirror images, but they are like that, okay, to each other. So they're not the same thing. So here also notice this, okay, look at this angle and look at this angle. That is how you know that you have a flip, a ring flip. So what happens is that when you do one conformation, here is we are starting with one conformer of cyclohexane. So here the pink hydrogens, which is the axial hydrogen, is on the top. When you do the flip, when you go to the other ring structure, that axial becomes equatorial. This carbon is this one right here. This axial was going up. This equatorial is also going up. Okay, that is pretty consistent. So your carbon number 1, I will say always have this one as carbon number 1. Your carbon number 1 on that structure becomes this as carbon number 1 now. Okay, and that is just normal. So again, when you see the video and you see the flip that I'm doing for you, I'll show you in there how that carbon 1 is actually shifting to become this carbon. Okay, that this carbon shifts down when you do that flip. So which means that these two conformations are not the same. Okay, so if you think that these two chair conformations are the same, they are not the same, because now suddenly you've taken a group that was axial, made it equatorial. I mean, that happens to everything, right? So all the pink hydrogens over here, they were axial, now they are equatorial, and then all the equatorials, which are the green hydrogens, have suddenly become axial. So you've changed the location just by doing a flip. Okay, so again, watch the video. So here I have cyclohexane, and this one is also in the video. Okay, so you can watch that, because if you have hydrogens, then you're like, okay, whichever hydrogen, I don't care, it doesn't matter. And honestly, it doesn't matter. When you have a cyclohexane, it doesn't matter. But as soon as you put a group on there, a methyl group on there, now suddenly things are going to change, because in one flip, the methyl group is axial, and in the other flip, the methyl group is equatorial. So at this point, when you start having groups, then the hydrogens start getting annoying. Okay, it's like, what are the hydrogens doing here? I've got too much stuff going on. I just want to focus on the methyl group. So that's what I've done here. And that's what I would like you to do as well, is to just focus on the groups, okay? You don't need to draw all the hydrogens out. Okay, if you do that, actually it's even more confusing. All right, so better not to create any confusion for yourself. So here's the methyl group going up as an axial, and then in the flip it's going equatorial. Now the thing is, which one is more stable, right? Because now you have these two different kinds of groups, equatorial and axial. So the equatorial is going to be a little bit more stable, because the equatorial group is actually out there with more space. Again, the video. Okay, watch the video to see it if you don't believe me. All right, because what happens in the axial is, if you look at this CH3 here, this is going to start interacting with these three, with the other two hydrogens, okay, on there. But if the CH3 is out here, then there is nothing to interact with. So which means that in this case you have some steric tension, but here in the equatorial there's nothing to stress about. You have enough space, okay, in there. Now in general, going from now until the end of the the chapter for cyclohexane, and even in future, whenever you're doing conformations, whenever you have the bigger group on the equatorial position, it's always going to be more stable. Okay, so you can take that with you all the time, is that the bigger groups should be in the equatorial position. All right. Here are some rules for writing conformers. Okay, so I've given you what is correct and what is incorrect. And this is just for your sanity and mine also, because when you give me structures, I want to be able to look at them quickly and tell you whether you're doing something right or wrong. Okay, so first of all, always start writing your substituents in the chair conformation on the top right. So always start your chair conformation like this, not like this. Okay, excuse me, not like this, as in not like this. Don't draw it like this. Okay, this is not a good way to get started. Always draw this conformation to get started. Draw your methyl group on this carbon. I said focus on this carbon as being carbon number 1. Okay, so this should be carbon number 1 always. Okay, and trust me on this one, because later on when we start doing reactions and whatnot, when we write structures out, this carbon is going to become important. Okay, so I'm not just saying it because I want to be everybody to write the same way. No, it's also for you. Okay, so your understanding is better. Okay, so start from that carbon, it will be better for you. Draw the first chair conformation as I have done. So this is kind of what I'm saying, is draw it like this, not like this. Okay, because if you draw it like this, trust me, it's a little bit more confusing. Okay, so this one is a better way to get started. All right, also start with the group being axial. Okay, that's it. So I told you the conformations I do for my Newman projections. Also, I keep the front carbon static and I move only the back one. Here also I'm telling you that when you start drawing the structure, start with your groups in certain positions, because that will really help you to see. Okay, later on also it will help you. Okay, so that was for the one structure. If you just had the one group on it, you know, so we talked about that you have equatorial groups that are going to be more stable. Okay, so now when you have two structures, two groups on there, so di-substituted cyclohexane, if you have two, then you can have a cis and you can have a trans. So if you have two methyl groups, then you can have a cis or you can have a trans. If you have 1,3-dimethyl, you can have cis and trans, so and so forth. Okay, so the next few slides cover, you know, how you deal with the two structures, because the cis and the trans, you know, they look very simple when you draw them in 2D, but 3D is different. So here's the one for 1,2-dimethyl. Okay, so we'll start with the cis, and we also have trans on the same one. So when we say that we have cis 1,2-dimethyl cyclohexanes, cis means they're going in the same direction. When they're going in the same directions, it means they're either going up or they're both going down. Okay, not that they're both going to be equatorial or axial. No, they're both going up or down. That's the main thing. And that's why we go through the hydrogens being axials and equatorials and up and down to show you what that means. Okay, because when we say that we have two groups that are cis to each other, it means they're both going in the same direction. Okay, so if you want to highlight that, you can highlight that for yourself to say that they're going in the same direction, and that is the cis. Okay, when they're trans, they're going to go in the opposite direction. Okay, so that's the main thing. It's not about being equatorial or axial. It's about directions. Okay, which direction are they going in? Okay, so then let's look at the first one, which is cis. And so here you have these two groups that are in the same direction. So they're 1-2 relationship. So here one of the group is going up axial, the other one is going up equatorial. Axial, equatorial. That's what I wrote here with A and E. Okay, so now when you flip them, the pink one comes down here. Remember, as I said, carbon number 1 comes down here. So that becomes equatorial, whereas the equatorial becomes axial. But both of them are still going up because they are cis. They were going up here also. They're going both up here as well. Here also axial and equatorial, both of them going up. Both of them are going to be equal in energy and stability because they're both the same. Why are they the same? Because one group is going axial, one is going equatorial, both are up, so exactly the same things. Okay, now let's look at the trans. In the trans, they'll be going in opposite direction. So one CH3 is going up, the other CH3 is going down. It happens to be axial and axial. So in the other one now, when you flip it, this carbon comes down here. So now the equatorial is going up and the other methyl group is also going down equatorial because the axials become equatorials. So now what happens? Now the equatorials are going to be lower in energy because we just talked about that if you put groups in equatorial position, they are less sterically hindered or less sterically strained, okay, because they have enough room to kind of spread out, okay, as you can say. So now in the trans case, you have, you know, the equatorials becoming a little bit more stable, but the cis was not as stable. Now, what does that mean for us? Okay, these kind of things have a meaning for us when we are dealing with reactions. Okay, like which compound is going to have more stability, which compound will be less, so which one will form more, which will form less. That's kind of where we're going with all of this. Okay, so let's go ahead and look at the next one now. So in the case of the 1,3, also we have the cis and the trans. So now you're understanding, hopefully this is a little bit better now. So 1,3 meaning this is a 1,3 relationship going both in the same direction. So the 1,3 relationship is both going up. So because one axial goes up, the other one goes down, the other one goes up. Okay, so this is an axial relationship. And then when you do the flip, the axials are going to convert into equatorials. You don't have to draw that out. Okay, so you know the axials are going to go into equatorials, and you don't even have to think too much because you know the equatorials are going to be lower in energy. So this is the more stable conformation for the cis 1,3. Okay, remember the 1, 2 was different, right? So, I mean, you just, the different positions, you know, of these groups, that's kind of what determines, you know, what's going to be more stable. Okay, the trans 1, 3, one is going up, one is going down. So here one CH3 is going up, the other one is going down. But in this case, since going, you know, the CH3, this is how I look at this, right? So one CH3 is going up, the next axial is down, the next axial is up. So since this is a 1-3 relationship, I'm going to stop here. So if this was going up, my group for the third carbon should be going down, which is equatorial. Okay, so axial equatorial, which means when I flip it, it will still be axial equatorial, which means they're both equal in energy. Okay, so not, again, nothing too exciting going on here either. You know, it was in the cis that was exciting. So it just depends on, you know, what the locations of the group are and what the direction of these groups are. That will help you determine. You can't memorize this. Okay, that's what I'm trying to say also. You have to kind of work it out. And then here is 1,4 dimethyl. So again, you can go through this yourself and you can understand how the cis and the trans is working. I do have a video for the 1,2, I think. I didn't write the link there. I will write it there. But the 1,2, I think I have a video for you that you can look at. So, you know, go through this. The next slide, before I go there, I just want to tell you, because I'm not going to be recording on that slide, is that slide is actually coming from a website from where you can actually draw molecules. It's called MoleView. I will provide you the link in the classroom, and so, you know, in your you know, PowerPoint somewhere. And that's a very good site where you can go and draw molecules and then look at the relationship, you know, how it is going to be in a 3D structure. Okay, so do that when you get time. You know, it's not very hard to use. You'll see it's very simple to use and very easy to visualize the 3D molecule in there. So that's that. I think I'm going to end over here. Nothing much going on. So I want to show you a trans cyclohexane, and so I'm just taking 1, 2 dichloro. So there's just chlorine, and this is trans. Okay, so we've taken cis and now we'll take trans. So this software, of course, is MoleView, and here I'm going to show you how you can move around this structure. So this is the cyclohexane, as you can see, and the trans is, of course, you can see the chlorine one going to the front, going to the back. So that's the trans. Okay, so now our thing is to see how it would look in a chair conformation. So just bear with me and I'll show you. So here is the chair, right? You can see that chair right here. And so now if you look at the structure, then you can see one of the chlorines is going right up, okay, over here. And this is going up as an axial. This is going down as an axial. And this up and down axial is trans, okay, to each other, which means that they're going in opposite direction, which is what it means in the case of cyclohexane. Okay, to be trans is to go in opposite direction. It doesn't mean that if one is axial, the other one is going to be equatorial. No, it's going to be that if one is axial, it can be that the other one is also axial, except now it's going in the opposite direction. So what is more important is the direction it's going in, whether it's going in opposite direction or the same direction. And the opposite is the trans. Okay, so this is the chair conformation. Again, here is the chair, and here's the chair conformation for a trans 1,2 disubstituted cyclohexane. And then the last thing here, okay, just remember all your keywords and whatnot, and that's it. That's it. That's where we'll stop.